Okay, we'll go ahead and get started. This is the Sunil Golwala Group. Our mentor is Karthik Ramanathan. I'm sorry.
It's all right. It's all right. I can take it away. Okay, fantastic. Okay, thank you everyone for being here. My name is Karthik, and I was the mentor to these two excellent students, Gabe and Kyle, and we work in the Golwala Group. So I just want to give you one slide overview of what the Golwala Group does. Basically, we are experimental particle physicists looking for something called dark matter. But dark matter is just a phrase for an unknown material that we believe permeates the entirety of the universe and makes up most of the mass of it. So we don't see it, we can't, there's no light that comes out of it, but then we can only see from its effects in gravity, or its gravitational effects. And so our group builds some of these particle detectors. They're just basically chunks of silicon, which we've instrumented with certain electrical contacts, these superconducting films on top of it. A picture on the top right for some of the stuff that we build locally. And we're also part of a larger collaboration called Super CDMS, which uses similar technology to build some kilogram size scale, these chunks of silicon instrumented with these electrical superconducting films. And so the project for the students, for Gabe, was project one. We wanted to test some new R&D devices in our dilution fridge, which is a device that gets these detectors down to very cold temperatures where they operate at. And so how do we mount them? And then the second project that Kyle tackled is we want to calibrate, i.e. understand the behavior of some of the other larger super CDMS detectors and what might the mechanical experiment or design of that experiment look like. And so with that, I'll turn it over to Gabe.
Okay, so I have my notes here. Okay. So how does someone design a holder for a dark matter detector? I hope it doesn't look too silly that I'm holding two. But okay. So first I'm gonna go through an overview of our current detector mounting system. So in the I've been developing two designs for a detector mounting system. And as Karthik mentioned, our group uses superconducting detectors to find dark matter. And the idea behind this is that the dark matter particle will interact with the silicon substrate of a chip, causing a slight change in the overall properties, electrical properties of the entire device. And that is seen by this little cartoon in the bottom, which is the sensor principle. These chips, like Karthik mentioned, only operate at extremely cold temperatures, so we have to stuff them in this awesome looking device on the left. And this gets up to just a fraction above absolute zero. Currently, there are two devices in our dilution refrigerator, which is the hexagonal box that you might have seen in the previous slide, and then also this 2 centimeter chip mount. So I was tasked with removing the hexagonal box temporarily and replacing it with a new holder for a 1 centimeter chip. So that brings me to my design one, which is a revised holder for the chip. Using a CAD software known as SolidWorks, I was able to design a revised holder for a new 1 centimeter chip. Some immediate changes to this design is that there is a need for multiple SMA connections, which are basically just electrical connections. And I'm not too sure, but this is the assembled box design in the middle. And yeah, so that's the assembled box design. The center is where the detector will be placed for the new 1 centimeter chip design, which is seen down below. And this box is also made up of 3 components. So the cover, the center, and then the bottom, where the chip will be placed in the bottom and like kind of sandwiched in between all the different parts. I guess one of the main challenges I faced with this designing process was like mainly just making sure that all the measurements were super exact and that everything fit together precisely. So yeah, and then here's the cool part that I thought was really interesting, was actually designing this box and placing it into the dilution refrigerator design that we have. So yeah, the problem was that we already had a previous design meant for the hexagonal box, and we had the space that we needed to fill. Luckily, the newer design fits directly in the middle of the hexagonal box design, so that problem was fixed pretty easily. And then finally was the adding of additional K250 parts, or basically, these are electrical parts meant to, I guess, input the right amount of electricity, electricity into the actual trap, or not trap, the actual design or the chip. Yeah. And so for future steps, I think our group will probably go ahead and 3D print the designs first for test fitting, and also the CAD models that were designed beforehand would need to be turned into schematics for actual metal manufacturing. I also wanted to go quickly over what I learned during this project. I learned a lot of the basics of mechanical and electrical engineering, so super excited about that. I was able to also learn how to use the SolidWorks program, which was a software I never used before. So I'm glad that I got to use a new software. And then finally, I wanted to thank Karthik and Brandon for helping me get situated in the SRC, and to all the people that made this possible, and everyone here for listening to this presentation. Thank you.
Hello, my name is Kyle, and I worked on something called the backing array for this project, which I'll explain in a minute. Starting with the overall science goal, the Super CDMS collab, which this group is part of, has these dark matter detectors, and they want to understand what a dark matter interaction response might look like under these detectors. So the plan is to use neutrons, which are hypothesized to have a similar response in the detector as to dark matter. How it works is when fired on the target nucleus, the neutron or the dark matter particle will deposit some of its energy on the nucleus, and we'll refer to that energy as E sub T. And it also rip off some of the surrounding electrons, ionizing them, and that will be referred to as the E sub E. The electron signal is actually what is measured, and the total energy deposited on the nucleus is not equal to that. And this mismatch is what's called the ionization yield, and it's what we're trying to understand. So the purpose of the experiment is to understand the relationship between nuclear recoil energy, E sub T, and ionization yield at E sub T less than 1 kilo electron volt, which this experiment is sensitive at. So our colleagues at Fermilab worked on an experiment that looks something like this. There'll be a neutron generator, so that's this thing that uses deuterium, which is hydrogen with an extra neutron, and that will fire a neutron beam at a silicon detector, and that's where the target nuclei are. And after it hits that detector, the neutron will scatter off into some array at the back. That is the backing array. And we expect the target energy to be some f of theta. So that means we need the angle at which the neutron has scattered at. And to do that, we will be using the backing array, which I'll explain in a sec. Also, we use some simulations to understand how the neutron scattering. So you see the generator back here that's firing neutrons at this detector, and the array will be way in the back there. And also, one key part of the array is scintillator bars, which are rectangular prisms that will give off light when hit by the neutrons. So we can measure that amount of light. And those glowing plastic things are the scintillator bars. So using the 3D modeling software SolidWorks, and in collaboration with my mentor and other colleagues, I made a design of what this backing array might look like. So you have these crisscross bars here. That is the scintillator bar that allow for accurate positioning of the neutron beam on there, and we also have these rings that will allow us to measure the scattering angle to the precision of a few degrees. And then also we need a holding structure for that backing array. So it's going to be mounted on this cart. So what I did is I took those two main beams off the cart, which are these, and extruded them 2 feet, and that will hold a bow tie shaped plate. down here that will hold the backing ring, which is highlighted for contrast. And to give you an idea about the scale, that this is about 6 feet tall. So yeah, and there are also supposed to be lead bricks on here, which lie like right below there. So finally, there are some improvements to be made. We need to hold everything together, so all the brackets, because everything is sort of free floating at the moment, and also improve on the adjustability of the design. If we need to move the neutron beam closer or further from the neutron source, and if we want to adjust where the neutron beam hits the thing. As for my takeaways, the most important thing that I learned was applying myself to adjust and revise designs to fit a certain problem. And as I would like to go into something like this, engineering research one day, I think that's a really important skill to have. I also learned about the applications of some of the stuff I'm learning. For example, learning why an LC circuit is useful using math. And overall, I was super happy to participate in this program. I'd like to say thank you to Karthik, Brandon, the other mentors, and the organizer. That's all. Questions?
Questions for either of our presenters? Any comments on their?
No, it's been a fantastic experience. They both picked up the SolidWorks software very quickly. And then, for example, Kyle has been participating in some of our phone calls or Zoom calls with Fermilab colleagues, and has really made an impact. And then the design by Gabe is something that we're going to actually manufacture. And so, yeah, it's been a really productive month.
Contributions, any questions?